I will start the recording here. At least the bar will not appear in the OBS version of the recording, so at least we have that. Okay, so our plan for today will be to continue discussing about this ammonia MASER, and then we have at least two people going to present, right? Is it Wenlan and Kaishen, I think? So we'll do that after the break. But for now, let us continue with the ammonia MASER. Okay, so yeah, you guys were saying like suddenly you learn a lot of new things, right? And we will be continuing on this. So what we have done is we studied the ammonia MASER. When we started, we studied the ammonia MASER by itself in vacuum, right? No electric field. We solved the Schrodinger equation. We found the eigenstates, and then we put a static electric field pointing in the z direction on this ammonia atom, and we did not solve the Schrodinger equation for that, right? Do you notice? What we did was we just found the energy levels, right? Because what we're going to do is we're going to generalize to the case where this thing will start to oscillate, and now we will start to solve the Schrodinger equation for this. But since this is a lot of new things, right, and you guys said you need to review and study a couple of things a few times, so let me at least recap a little bit of what we have done so far. When we solve the Schrodinger equation, we have found the eigenstates of the Hamiltonian, and I have explained last time that eigenstates correspond to the stationary states, right? Did I press record? Yes. And here? Okay. Oh yeah, Jia Cheng, not Kai Xuan. Sorry. Okay, yeah, so now is the you and Wenlan, right? Okay, so we want to find the we have found the eigenstates, and we have found the states like this, and when we solve the Schrodinger equation, we have found the eigenstates of the Hamiltonian. And the Hamiltonian, once we got the eigenstates of an operator by the postulates of quantum mechanics, we can use them as a new basis. So the new basis we have found to be, I will label them as Roman letter 1 and 2, right? So the Roman letter number 2 is 1 over square root 2 of 1 plus half. So this is a superposition of these two states. So superposition state is very hard to draw, right? It's like being both this and this at the same time. And the other state is Roman 1, 1 over square root 2, and then it is the difference of the two states. So I can convert from one to the other. If I solve this simultaneous equation for state 1, I can convert this back in terms of Roman 2 plus Roman 1, and then this is state number 2 can be expressed in terms of 1 over square root 2 Roman 2 minus Roman 1, right? So it's just solving simultaneous equation for each other. So this is what we found last time. These are the eigenstates of the Hamiltonian, these two, right? So once we have found the eigenstate, what we wanted to do was we express the ammonia molecule using the new basis as follows, right? So originally the state was an arbitrary, any state is written as a combination of state number 1 plus state number 2, right? But 1 and 2 can be given in this form, so I got C1 over square root 2, state number 2 plus Roman 1, and then C2 times this is C2 over square root 2, Roman 2 minus Roman 1, right? So you collect and arrange all your constants together. What we have found is that is C1 minus C2 over square root 2, Roman state 1, and then C1 plus C2 Roman state 2, right? And constant minus constant is still a constant, therefore we will call this constant big C1, and this constant shall be called big C2. All right, so my quantum state using the new basis is just C1 Roman 1 plus C2 Roman 2. Okay, so we have expressed everything in this form, and at the end of our previous class we have derived the Schrodinger equation in the new basis and in this electric field, right? So Schrodinger equation in the new basis is given as follows, right? So I don't want to go through the details again. We have done this at the end of previous class, right? So you can check the video or you can check the class notes, but what we have stopped last time was until here, and then plus P times this, and then C1, and then IH bar, the second derivative of the coefficient, is equals to E0 plus A C1, and then I got plus P E C2. Okay, so this E is the electric field, and this electric field is oscillating with time. So this is a changing function of time, and then this. So this is now a coupled ordinary differential equation, right? So the C1 is C1, C2 plus C1, right? This is C1, and then plus C2. So this two term is the one that spoils everything. It makes it difficult to solve, right? So these two terms couples the ODE. That is the problem. Right? So this will make it depend on this, and this term will make it depend on this C1. So that is the headache that we want to deal with for today. Okay? So that was a very quick recap of everything about the ammonia MASER, right? Last time. Now we will continue and try to solve. So for the math student, right, you might not like the way we were going to solve this problem, because we are going to make a lot of assumptions and a lot of approximation, and we're going to throw away a lot of terms just so we can find some solutions. Okay, but we are going to get started. Okay, any questions? Yeah, right. Jia Sheng was the one who presented the very first. Were you the very first person to present? You can present more than twice over the semester if you want. No, I'm not gonna stop you, right? But everyone present at least two. If you want to present more times, even better. Okay. Yeah. Should I give bonus marks for presenting extra? I don't know. Let's think about this later. But for now, let us figure out how to solve this problem. Okay. So like I said, the math people will not like the way I solve this, because I will make a lot of approximation. But let's see how to solve this equation. Well, like I said, right, these two extra terms spoils the solution. And in fact, we have already solved, when these terms are zero, right, we have already solved this, right? So these are the eigenstates of the Hamiltonian. So the answer is just exponential times the state, right? The solution is an exponential. So we have solved this before. So let me write this just to remind ourselves. If this term is equal to 0, right, we would have this differential equation, which is way simpler. Or in a way, I call this a diagonal differential equation, right? So we call this a decoupled, because they C2 appear in their own equation, C1 appear in their own equation, right? So these are called decoupled. And decoupled equations are easy to solve, because C1 is integrate this, we'll just get an exponential, right? So C2, and then if you integrate this is a first order ODE, right? You get negative I E minus A T over H bar, right? And then there's a constant, so I will call this constant gamma, right? So this is gamma for this solution, and this one integrate also, I will get C1, and also a constant gamma 1 e to the power of minus I E plus A T over H bar, right? So this is equation 3, this is equation 5, and these are my constants, right? So this was our E equal to 0 solution earlier, right? When we started, we consider a ammonia atom by itself, no electric field. So we actually found this solution again. But now, yeah, this was like, oh, how nice would it be if the electric field is 0? Then it would be so easy to solve. But unfortunately, the electric field is not 0. So if E is not 0, so how can we solve this solution? So here we are kind of following the Feynman's approach in his textbook. So what we do is, okay, if this is not 0, but if it's small enough, right, if the value is small enough, it's just a slight change from non-zero, then we expect that the solution is still similar to this, right? Because if I just increase it, electric field increase from 0 a little bit, then the solution might change. But if I increase a little bit, then the solution should only change a little bit. So if it only change a little bit, then we can make some assumption about this. So we shall try to assume this solution is still looks like equation 3 and 5. But how can it be? Right now I got extra term, so I need to modify the solution from here. So what we try to say is, okay, if this is not 0, then maybe this will be depending on time, right? So maybe this will depend on time, because our previous differential equation, this is a time dependent differential equation, right? So this function changes with time, right? Because it's oscillating with time. We wanted to say that, oh, if this is 0, then my solution was this. But if now this term have time dependent functions, then we still want to say it should kind of look like this, very similar to this, but it might depend on time. So my gamma 1 and 2 depends on time, right? So but gamma 1 and 2 now depends on time. Okay, so that is what we try to claim. It's like totally not rigorous, right? There's no proof or things like that, but we just, okay, let's just try. That is kind of like the physics way of solving equations, because in most situations that is the only way we can make any progress, right? Otherwise we can't do anything. Okay, so so that is the situation that we have. So that means, for example, right, my C2 solution over here, it was originally gamma, right, and then times the exponential, right? So times the exponential of IE0 minus A t over h bar. But now gamma depends on time. So if I try to plug this into my differential equation, right, I calculate dc dt, what happens? Let's try to differentiate. So dc dt, let's differentiate the exponential first. The exponential will be minus I will bring the I downstairs, so I got 1 over IH bar, right? And then I got E0 minus A, and then gamma e to the power of IET over h bar, right? But I differentiated exponential, but now I need to differentiate this as well. So I use the product rule. So this is d gamma number 2 dt, and then e to the power of minus IE0 minus A t over h bar. Okay, so I will try to plug this into my Schrodinger equation, see whether I can get a solution or not. So let's try and find out. Let me factorize the exponential out, so that, and also factorize the 1 over IH bar, so that I got E0 minus A gamma 2, and then plus IH bar d gamma 2 dt, and then the exponential go outside, h bar, right? So wait, this is equation 3, equation 4, so this is now equation 5. Okay, so this is what I did by manipulating C2. So we can do the same thing for C1. I shall not repeat everything. It's kind of the same, but essentially you will get this. You factorize out 1 over IH bar, and then you got E plus A gamma 1, and then plus IH bar d gamma 1 dt, and then the exponential, but the exponential for number 1 is e plus a over h bar. Right, so this is equation 6. Okay, so everyone follows so far? Right, all I did was I just say, okay, what if this is time dependent? Then this will be my derivatives. Okay, 2 is enough. Yeah. So now, especially those, yeah, you for those who have been experiencing both the math and physics side of doing things, right? So you see the different philosophy, right? Because math in the world of mathematics, you know, mathematicians are interested in math, so they're just solving puzzles and axioms and things like that. But right now, right? Remember what we are doing. We are trying to build an ammonia MASER. So imagine like someone is waiting for us to deliver a product called ammonia MASER, right? So we need to do something, otherwise we are stuck here forever, and then we owe somebody a device that we never deliver. So this is like the choices we need to make, right? So we try to do something to try to get some solution out. Okay, so let's try to continue a bit further now that we have the derivative over here, right? And I want to make this functions solve my differential equation over here. Okay, so let me just write this for completeness. Okay, so we got this situation now, and then let's see how to solve. That means what we do is we take equation 5 and 6, right? We got the derivatives, we plug the solution into here and all these functions here, and see whether left hand side is equal to right hand side. So let's start with the C2 differential equations. So we substitute equations 5 and 6 into the C2 equation, was called 1, right? So equation 1. So on the left hand side was all our stuff here. So on the left hand side is IH bar times this. So IH bar times this will cancel away the IH bar, d gamma dt, and then I got e to the minus IE 0 minus a t over h bar, and then on the right hand side is this times C2. So is e minus a times C2 is just gamma 2 e to the minus I this thing minus a t over h bar, and then plus PE, right? So this E depends on time, but it also depends, and then times C1, right? So that's the C1 coming out here. Okay, so I can't even cancel the exponential because this is plus, this is minus, right? So these two are the same, but this last term at the back is not the same. Okay, so what we can cancel is, yeah, these two have the same exponential. This is E0 minus A gamma 2, E0 minus A gamma 2. So these are the same term, so I can cancel this term, right? So I can cancel this term, and then what I'm left with is d gamma dt, right? So simplify IH bar d gamma 2 dt, and then I shall bring the exponential over to there. So this term cancel already, right? So this is PE gamma 1 e to the minus IE plus a t over h bar. That's the exponential. I bring this over, so this becomes e positive e naught minus a t over h bar. So if you look at the exponentials, the e will cancel each other. Minus IA minus IA. So on the right hand side is negative 2IA. 2IA t over h bar, and then IH bar d gamma 2 dt, right? So I have, well, it seems that I did not make any much progress. I started with one differential equation, I ended up with another, but at least on the right hand side there is only one term. So maybe we can do something about this. equation instead. Okay, so we have this differential equation now, but we have also a second ODE, right? So we substitute 5 and 6 into equation 2. Right, so just now 5 and 6, just now substitute these two into 1, I got this. Now we do it into equation 2, and then we get similarly, right? So I will not show you the details again because it's the same thing repeated. But when you are studying, probably you should try to work it out yourself, right? As a practice. Okay, so you got, now it's positive 2IAT over H bar. So you try to work it out yourself and try to recognize that this is positive power and this is a negative on this side. Okay, so now let me try to simplify a little bit, right? So there's a 2A. There's a 2A. So, and remember, right, what was 2A? So 2A was the, recall that 2A is the energy difference between states 2 and 1 in vacuum. Right? So that means if it's convert from an excited state to a non-excited state, then it will release a photon, right? So if the atom transitions from state 1 to state 2, it emits a photon of energy 2A is equals to h bar omega, and this will be the frequency of the emitted photon. Well, angular frequency, right? So because of this, let us write 2A is equals to h bar omega 0. Okay, then our equations will be expressed in terms of this. So what was our equations here? I got IH bar the gamma number 2 dt, and then I got PE gamma 1 e to the power of minus I omega t, right? And then my second equation was IH bar d gamma 1 dt, PE gamma 1 e to the positive I omega t. Right? So I got this now, and then what else should we do about this? Well, now we try to solve this time dependent equation. Remember, this depends on time, right? So this E, right? So this E is a function of time, and it is equals to E, what was it? I omega t plus E minus I omega t. Okay, so then the equations is actually let's write this here, right? So the gamma 2 dt. So I substitute this thing into here. So I got a PE naught, and then this is exponential, right? So this is exponential omega t times negative omega. So this is I omega minus omega t, and then this is negative, so let's put negative omega plus omega t, right? So that is minus omega, and then the same thing here. This now becomes the gamma 1 dt, and then I got PE 0, and then this is e to the power of I omega plus omega t, and then plus e to the I omega minus omega t. Okay, so I got this solution now. So does everyone follow the story so far? Right? Maybe if it's a bit too fast, but it's just manipulating, right? So is something that you should be studying later. Yeah, so speaking of which, the next part will anger Tao Xuan even more, because wait, where's my, this is page 1, this is page 2. We substitute now, this is page 3. We do another approximation, right? So yeah, so it would be nice if we like follow, you know, Taoshan and get an exact solution of everything and get a proper solution. But for now, we just want to get some solution, right? We just that is also another difference between, you know, math and physics. Is math, you know, the philosophy behind math is to find all the solution and all the solution that exists for every case, right? But for us, for now, at the moment, just for the moment, eventually we should go to math and get all the solutions. But for the moment, right, we just want to build a MASER. So we need something to start building the MASER, right? So that means what we're going to do is, I'm going to make an approximation. Okay, so approximation is to say that, okay, I want to throw away these terms. Again, actually, I come back with a coupled ODE again. Well, not coupled, but it is a differential equation with many terms. Okay, so what I want to say is that, wouldn't it be nice if hang on, yeah, there's a gamma 1 I forgot to write here, right? So there's a gamma 1 here, and then there's a gamma 2 over here, right? So gamma 1, gamma 2, yeah, this one is important. So it is coupled, and then we have a differential equation with many terms. Okay, so since there's so many terms, then we ask, you know, the physics way of doing things, like, wouldn't it be nice if this term is not there, and then I'm just left with this, and it's easier to solve, right? Then and then one of them is also not there, and it's easier to solve. So it's always easy to ask, oh, wouldn't it be nice? But we must justify why we argue these things. So the way we argue this is that omega, this is relatively larger than omega minus omega 0, right? So something plus something gives you a huge number, right? So if this is true, then we will study the case that I omega t, right? Remember, exponential of I something, complex exponential is sine and cosine. So if this is a large number, then this will oscillate very fast with time. So this will oscillate rapidly around 0. Right? So that means this term is negligible. So it averages to 0, and therefore it is negligible. Okay. So yeah, so this is one of the non-rigorous and very non-mathematical way to do things. Why people in physics do this is because, yeah, we are building a machine and device. So function that oscillate rapidly, right, may not be detectable by experiment. So if it's not detectable by experiment, there's no point keeping the term there. So that is why. Okay. So that is why you can, we say that this is throwing away to 0. So my equation approximately becomes I h bar d gamma 2 dt is equals to p e, and then you got gamma 1, and then exponential of I omega minus omega 0 t, I h bar d gamma 1 dt. This is p e gamma 2 e I omega minus small omega t. Okay, so we have arrived at this equation. Okay, so actually, after doing all this, it is still pretty difficult to solve, right? So how do you integrate this differential equation? This is coupled. You can, but it's gonna get very messy, right? But actually, still always remember our priorities. Our main job is to build an ammonia maser, and we just need the ammonia maser to do one thing. It's just to emit the photons of h bar omega, right? And it would be enough if we further focus on a case where I make this equation even more simpler, right? So furthermore, we focus on the case where omega is equals to omega 0, right? So this is what we call the resonance. Okay, so the oscillating frequency of my electric field is equal to omega 0, right? It's resonance, right? Omega 0 is, we can say, is the natural frequency of the system. It will be the frequency emitted by the photon, right? So if omega is equals to omega 0, then this term will be 0, right? Then what happens is, page 4, what happens is, well, my two equations become this. So my IH bar, the gamma 2 dt, is equal to PE gamma 1, and my other equation is the gamma 1 dt is equals to PE gamma 2, right? So we are making all sorts of excuses and reasons to simplify our equation. Finally, we get to this point, right? But when we make excuses, we always remember what were the reasons. So we always remember we are in this case, right? So we cannot assume these two are different, then our solution doesn't work anymore. But when we're remaining in this case, then yes, we can find a simple solution. Well, notice that this is gamma 2 times gamma 1, right? And this is gamma 1, and then there's a gamma 2. So if I differentiate both sides of this equation, I got the derivative of gamma 1. Then I can substitute into here. Okay, so let's differentiate both sides of the equation, and we can now solve this. Okay, so E naught is the amplitude. Okay, so second derivative. Like this. Okay, so yeah, let's how do we do? So let's bring the IH bar to this side. So wait, before I bring this, notice, okay, so now we got this, right? I can substitute this into here. Okay, so we notice that this is equals to IH bar d2 gamma dt. Well, if I bring this down, right? So I bring this down, I got 1 over IH bar, and then I got P square E square, right? So I got PE, I'll write the full steps. So PE over IH bar, and then this is gamma 2. Okay, then this IH bar I bring down as well. So the I times I will become minus 1. And then PE, so it becomes square. So I got P square E square over H bar square gamma 2. Right? So yeah, so now I got this differential equation. Gamma 2 and gamma 2 second order. So everyone knows how to solve this. This is very easy to solve. Okay? If you are not, hang on, what time are we now? Any question? Okay, so I guess your brains are fried, looks like. But so I guess let me show one more step. Notice that this is the gamma dt, right? Gamma 2, and this gamma 2 is over here, so I will substitute into this expression. So I show you the details again. And then this is PE, and then after substitute, this is PE0 over IH bar gamma 1, right? The IH bar I bring down, so it becomes a I times I becomes a negative. This is P squared E squared over H bar squared gamma 1, and this is just the second derivative of gamma 1. So finally, we got a solution that is pretty easy to solve, right? So our solution was the solution is the standard ODE, right? But so let me call this hang on, let's get this solution first. Okay, so it is going to be a constant cos and then the square root of this thing, right? So it's PE over H bar T plus B sine PE over H bar T, right? And then I got another solution over here, but the same thing, but the constants, well, C cos PE over H bar T plus D sine PE over H bar T. Okay. So we got the solution now, but the constants, there is a relation between constants CD and AB, because they must satisfy the original ODE. So in particular, right, well, they must at least satisfy this, right? So let's write this down again. So let's check whether the left hand side is equals to right hand side or not. So this was my differential equation that we got here, and that is the derivative of gamma. So now we find that IH bar, if I differentiate this, I got negative PE0 over H bar A sine, right, PE0 over H bar T. And then if I differentiate this, I get plus PE0 over H bar B cos PE0 over H bar T, right? And then on the other side is P times E and gamma 2. So this is PE, and then C cos PE over H bar T, and then PE D sine PE0 over H bar T, right? So we cancel the H bar here, right? And actually everywhere there's a PE, so I can cancel everywhere here. So what do I find is, I find that I got negative IA sine PE0 over H bar T plus IB cos PE0 over H bar T, and then this is C cos PE0 over H bar T plus D sine PE0 over H bar T. Okay, so I can compare left hand side to right hand side. See, cosine, cosine. So these two must be the same. Sine and sine. So these two must be the same. So comparing both sides, we have found C must be equals to IB, and D must be equals to negative IA. Okay, follow so far? Oh. Yeah, so I guess Jia Cheng already said. Yeah, the Euler formula, yes. Okay. Where am I? So I got, this is page 1, this is page 2, this is page 3, this was page 4. but we got the solution now, right? So let's compile our solution at the end of the day. Let's see what we have. So we have gamma 1, right? So gamma 1 is a function of t. So our solution for gamma 1 is a cos PE0 over h bar t plus b sine PE0 over h bar t, and my gamma 2 was gamma 2 is c equals to ib, right? So it's ib cos PE0 over h bar t minus ia sine PE0 over h bar t. So this is just the gamma, right? And remember what was my solution for C1? So C1t was gamma times the exponential. So it's actually all this bunch of stuff. So it's let's put the exponential a t over h bar, right? So times gamma 1 so it's just I e0 plus a t over h bar, and then the gamma 1 I shall write it here, plus b sine PE0 over h bar t, right? And similarly, my solution for C2 is now equals to I, that's a negative exponential, E0 minus a t over h bar, and then it was IB cos PE0 over h bar t minus IA sine PE0 over h bar t, right? So we have found the solution finally, right? After all the assumptions and excuses that I make to try to argue the solution, where let me at least write down what to remind ourselves of our assumptions, right? So we argued that for small electric fields, right, and then rapidly oscillating EI big omega plus omega 0, right? So this is close to 0, and at resonance omega equals to omega 0. The solution is, well, my state evolving across any time is given by, remember how did we write the state? It is C1 plus C2, right? So C1 plus C2, right? So my C1 is all this stuff here. So let me write all this stuff here. So my C1 is exponential of minus IE0 plus A t over h bar, and then A cos PE0 over h bar t plus B sine PE0 over h bar t, and then this is state of Roman 1, and then plus this state. So this state has an I here, so let me put the I here, and then I e negative a t over h bar, and then this is B cos PE0 over h bar t minus A sine PE0 over h bar t, and then this is state of Roman 2. Okay, so finally, after all this trouble, we have got our solution. Okay, so, and if in fact this is a very long solution, and it's under a very, very special case, under very, very special assumptions, right? So again, the difference between physics and math, right? Physics is just like we want to find one solution for a very specific purpose. Usually in math, there's no specific purpose, but they just want to solve all the possible solutions for all the possible cases. So one broad approach, and another is very deep but specialized approach. Okay, but it would be good if you are able to get the broad and general solution for every possible case, but it seems we do not have the skills or knowledge to do that yet. I don't know. Maybe I should try to ask Taoshen to get a solution to this, see if we can do it or not. Then we can do more special cases. But for now, we get a resonance, right? So if my electric field oscillates at the frequency of omega 0, And what was omega 0? Omega 0 is this number. If the electric field oscillates at exactly this frequency, then I know my solution over here. Okay, so let's call this equation star. And we got our solution. So what time are we at now? 9:49. Okay. Well, it depends, right? But it depends. But you can always reason out. You can always reason out the situation, because you always remember that exam is always 2 hours. So questions are supposed to be solved in 2 hours. So we spend almost 1 hour doing this. So probably not the whole thing, but maybe you can solve part of it. I don't know, right? I have no idea. But when you study for exam, definitely it is worth like working through and understanding how to get the solution. And the reason why we are covering this in the lecture is not really for tests, but for your knowledge in the future, right? So remember, we are here to train to become physicists, right? And these are one of the things that in physics we need to do most of the time, right? So suppose that someone wants to build an ammonia maser, this is part of the job, right? But we haven't, okay, we are almost there to build the ammonia maser, right? We're pretty close. The essence of physics is approximation. Yes, Zihao, that is true, right? Because most of the problems that you see, right, whether in math or things like that, you know, the questions are easy to solve and the solutions are very short. But in real life, like this is one of the real life problems we started to solve, right? The equation is so messy. There's so many factors to account for. You can't really solve it unless you use a computer simulation to solve everything, right? But if you want to do it like this, then you cannot avoid approximation. Yeah. So the engineer is the even worse, the next level of approximation, right? Pi equals to 3, that kind of thing. So yeah, we are still quite early, I think, relatively. Maybe I should talk a little bit about the ammonia maser, right? So I keep saying our job is to build the maser, but this is just the theoretical part. So now let us see how a maser actually works. So this is in the next part, 2.2.4, operation of the ammonia maser. Right, so now we realize, okay, why are we solving Schrodinger equation for an oscillating electric field? Why in vacuum, and why did we calculate this, and why did we calculate stuff like this? So now we see how. Okay, remember what is the purpose of a maser? Maser is the earlier version of laser. Laser is like shooting a beam of light or photons. All of them have the coherent frequency. And we can generate coherent frequency because the transition of my energy level is exact, as all the frequency is having this. So the maser is because we want to create, to generate photons of energy using the transition. Right, so this one is like when a quantum state changes from a high energy to a low energy, higher energy, lower energy, then the difference, right, will be the difference in energy is emitted in the form of a photon, right? So how can we do this? Okay, so I want to create a machine that can generate a stream of photons, all of them using the same frequency. And we know that when a molecule changes energy state, right, the frequency is exactly this. So the photon emitter is this. So that means what we want to do is we want to encourage a bunch of ammonia molecules, all of them in this state first. We try to create all of them in this state, and then we make them transition into this state. So if we can do that, then we can create a beam of MASER. Okay, so first of all, well, we need to create a state of this. Alright, so we need to create a beam of ammonia molecules, all of them in this state. And we have done something similar before using the Stern-Gallac experiment. Right? So this is similar to the Stern-Gallac experiment. So we emit a beam of photons, right? It could be any state. Okay? But we pass it through a selector. Right? So I will select all the states of Roman 1. Okay? So Stern-Gallac is using magnetic field, but this is the same situation using electric field. Okay? So I use the Roman 1 selector. So all the state that come out here is a state of Roman 1, right? And then whatever that is in Roman 2 will be discarded. Right? So all of these will be entering, all the beams that it generated will be having this state of a higher energy. Okay? So I got this state already, right? So that means I have all this state at Roman 1. But how do I make this transition? Well, I make use of this solution, right? So this is why we solve this solution. So if I enter a cavity with an oscillating electric field, right? So I have a cavity with an oscillating electric field. Right, this is what we call a cavity. So if you talk about laser design, right, they always mention some cavity, and this is where the photon creation takes place. Okay, and why did we solve this equation is because, well, if my photon enters this at time 0, that means my initial state is state 1. So I can fix my constant like this. Okay, so this is at time 0, it enters, the state is psi 0 is equals at Roman 1 at time 0. Okay, so I want to create the cavity such that when it comes out, right, because it's traveling over time, so it's traveling over time, I want to come out and I want to create a state that comes out with 100% probability in state 2, Roman 2, right? So if it enters at state 1 and comes out at state 2, that means it has emitted a photon of h bar omega inside here. Do you guys follow the process? Right? This is the design process. Okay, so if it enters at state 1, it's a higher energy state. Okay, and then this will evolve over time. We got the formula already, right? If we got the formula, it evolves over time. Then all we need to do is just to find the combination such that when it comes out, I want to be 100% in state 2. Right? In other words, my psi t out when the time it comes out is equals to 1. So I just need to design the cavity to make sure this happens. Okay? So does everyone follow so far? Right? So I hope you find this interesting, right? So we are kind of like this is kind of like the combination of all different branches of knowledge. We use math, ODE, even though we like violated it a little bit and make Taoshan angry, but we solve some ODE to get the solution, right? We use our knowledge from our Stern-Gallac experiment, manipulating the electric field, the selector, right, to do this. And then this part is gone. So this is experiment. It's also an engineering kind of thing, right? So design and things like that. In the lab, you have seen the videos, right? Like people be doing some optical tables work and things like that. And finally, we can create something that can emit a coherent photon source. Okay, so we have one last problem to worry about, is how to make sure it enters at state 1. We know how to do this part already using the Stern-Gallac setup, but how do we make sure we guarantee it comes out in state number 2? right? This is a quantum process, it's a quantum transition, but we need to guarantee this to be 100% probability so that I got enough photons to be generated. Okay, so we will take a break, 10 minutes break. After the break, we will have some presentation, and after that, if no one left to present, then we shall continue this story, right? How to fix this problem. So let's take a 10 minutes break. No, it's not a flipper, it's the selector, right? Flipper is just state 2 flip to state 1, state 1 flip to state 2. Yeah, so we come back at 10:10 and then we start some presentation. So meanwhile, I will stop the recording. We'll record here and do the full screen. Okay, so is it too bright? Yeah, so now my turn to present. Okay, so we are almost done building the ammonia MASER. Is it running? Yes. Now recording, yes. Okay, so just to recap and remind everything a little bit, right? So what we want is we want to generate all the photons of the frequency h bar omega, right? So we want to collect all of them in a cavity. So the way to do this is like the earlier questions that we just saw, right? An arbitrary state will pass through a selector, right? Not a flipper, selector, but the selector will select the Roman up state, right? So whatever this is, let us imagine is selecting this state. So in selecting this state, all of them will enter the cavity, and inside the cavity, it is connected to some electric power source, so it will generate an oscillating electric field, right? We even learned this in the electromagnetism chapter, right? But how do we do this? But for now, it's just that we just know that the electric field is oscillating back and forth along the z direction, and the general case for a general atom in this oscillating electric field, we have solved this already, but we need to make many assumptions. Okay, our last task that we want to do is we just want to make sure that the atoms come out with 100%. Oh, sorry, my screen. Oh yeah, because other people were sharing screen. I need to share mine. Yes, okay. Is it? Double check one more time. Yes, okay. So we just want to, inside the oscillating electric field, just now I was saying, I just want to make sure that the atoms come out in 100% probability that it is in state Roman 2. So how do we do that? Well, we got the general solution already. So let us see how to solve it. Okay, so like I said, right, this is, I will call time 0 the moment the atom enters the cavity. So when the atom enters the cavity, it is in state 1, right? So that means I can set this as time 0 and use this to determine my constants. So when the atom enters, wait, am I still sharing screen? I am, right? The bar on top disappear by itself. I don't know why. Well, that's good. So when the atom enters the cavity at time equals to 0, it is in state 1. So this is my state side. So that means in equation star, right? So this is a general case, but now we know that it is in state 1. So in equation star, my state at time 0 is equals to state Roman 1. So let's see what happens on the right hand side when I plug in t equals to 0. So it's very easy, right? When time equals to 0, it's just 1 times A plus 0 Roman 1, and then when time equals to 0, I got I times 1, and then B minus 0, or state Roman 2. So if I want this to be state equals to 1, then this will give me, well, it just gives me B equals to 0 and A equals to 1. Then when A is 1, then the state is normalized, right? So A equals to 1, B equals to 0, which means that my state at time t later, the state is given by psi at t, right? So now I know A is 1, B is 0. So at any time t later, I know B is 0, A is 1. So it is given by e to the power of I E0 plus A t over h bar 1. So it's cos P E0 over h bar t. This is state of Roman 1, right? So at time 0 is purely in state Roman 1, but as time goes on, this state will start to appear. So this becomes minus IE, minus, right? Yeah. So minus IE minus E0 minus A t over h bar sine PE0 over h bar t. This is state Roman 2. Okay. So yeah, so this is my state now. So remember what we are saying just now. I want to make sure it comes out 100% probability in state 2. So we want to calculate the probability in state 2. So the probability of atom in state 2 is what? Well, I want to calculate the probability is in state 2, right? But obviously it's going to be a function of time. So let us calculate this as a function of time. And we use our standard way to find the probability, right? So we do this, okay? That means we close this state with state number 2. And I guess I will just, do I need to write everything? No need, right? You know what I'm talking about. Let's just write this one more time. Right, so what I have is E minus I E0 plus A t over h bar cos PE0 t over h bar. This is state number 1. And then minus I E minus I E0 minus A t over h bar sine PE0 t over h bar state 2. Right, so this is a bracket, and then I take the absolute value of everything. So it is just state 2 multiply into this bracket. This term will disappear. They are orthogonal, right? They are not the same state, but this times this equals to 1. So I just end up with minus I E0 minus A t over h bar, and then sine PE0 t over h bar square. And the absolute value of this is equals to 1. So at the end of the day, you just get sine squared, right? So a very simple solution, E0 over h bar t, right? But this is a oscillating function. So this is P1 as a function of t. So the probability of finding the state in, what is the chances of finding the state in number 2? It depends on what time you measure it. It depends on t, right? So this is kind of similar to what we got earlier. Now it is a sine square graph, right? So the probability of finding it in state 2 is a sine square. Right? So what we want is, remember our mission. Our mission is to build the ammonia MASER, and the ammonia MASER, what we want is, I want to be 100% probability in state 1. So that means this part is important, right? Either this or this or this, but let's look at the first one first, right? So this part is important, right? So this is the time where this is in a 100% probability. So in other words, in this time, there's a 100% chance atom is in state 2. So if it's 100% charged in state 2, that means it entered in state 1, then in this time is 100% chance in state 2, this also lah. But then this is the time that we want, right? So this is the time that we want. So this is PE0 over H bar. T is equals to, how do we get probability equals to 1? It is odd integer over 2 times pi, right? So let's call this 2k minus 1 over 2 times pi. Okay, so if I solve this for t, right, so I'm solving this for t, I'll just bring this over. So I got 2k minus 1 pi h bar divided by 2 PE0. Okay, so I got this answer now, right? So how do we use this to answer our question? Well, this is the time, right? So this t is so if we let t be the time spent in the cavity, right? So we let t be the time the atom spent in the cavity. Okay. Okay. And also, well, we shall let v be the velocity of the atom. And then L is the length of the cavity. Okay, so now we see how the ammonia maser works. So my cavity, right, is this long. Okay, so it's coming, the atom comes in at, so it is in state 1, we know. It comes in at velocity v. So how long does it spend inside this cavity, right? So the time spent in the cavity right is, well, if we assume constant, then well, v is equals to L over t, right? So the time spent in cavity is t is equals to L over v. Okay, so if the time, so this, now we know if I build the cavity, it is this long, and if I somehow know the speed of the atom caused by the beam, then I can know the time spent by the cavity, right? So the state that comes out, well, it depends on the time spent by the cavity, and it will tell you what is the probability, right? So it will tell you ultimately what is the state that comes out at time t. So now we know, right? So if atom spends the time t is exactly equals to 2k minus 1 pi h bar over 2 PE0, then there is a 100% chance it exits the cavity in the state in Roman 2, right? So this is what we want, right? So what happens is it enters as state 1, exits as 2, right? So there's a energy change. Because in state 1, if you remember, the energy we have calculated in state 1 was E plus A, right? The energy of state 2 is E minus A. It comes out as a lower energy state. Right, so lower energy state. This is page 6. Next page is 7. Okay, so what I'm trying to say is that if I purposely have my cavity length is L equals to Vt equals to this T, which is 2k minus 1 pi h bar V over 2pe0. Then all atoms entered at state 1 and it exits at state 2, right? So in particular, because state 2 is a lower energy state, that means where did the energy go, right? I come in at higher energy and then I come out less energy, right? It has lost energy. Okay, so like this, like everyday example, right? So if you give me $100, I go to a shopping mall and then I come out of the shopping mall with no money. That means I have lost $100 inside, or I have spent $100 inside, right? Or 100 ringgit inside. So that means each atom has lost energy. What is the difference between energy? So let me write this down one more time. The energy of state 1 is E0 plus A. The energy of state 2 is E0 minus A, right? So what is the difference between the energy? It has lost the energy of E plus minus E minus is equals to 2A inside the cavity, right? It was emitted as photons, where 2A is equals to h bar omega 0, right? So this is the angular frequency of the photon. Okay, so that is how we get our ammonia maser, right? So we have collected photons, coherent photons of frequency omega 0, right? So we got the maser. At least this is a very simplified description of a maser. Yes, it's still able. Actually, yes. So if we, after it exit, right, then it will still follow the Schrodinger equation. If we exit the cavity in a vacuum, then it will follow the Schrodinger equation in vacuum, right? But it will follow after that. But the initial condition after that is in state 2. So the main point is, what happens after that, it might vary, but the main point is it exit. We know that the point of exiting is in state 2, right? Because of the Schrodinger equation and because of all the solution, it's 100% probability. That means we know there's 100% probability of energy being lost inside the cavity, and therefore there's a 100% chance of photons emitted inside the cavity. After emitted, it will do something else. It doesn't really matter anymore, right? The main point is we got the photon. Okay, so what is happening here is, let me summarize our situation, right? So we have an arbitrary NH3 beam, right? It could be any state, but we put it through a selector, right? So we put it through a 1 selector, right? So that means the state number 2 is, like you said just now, kick out or discarded, right? But the beam that comes out, everyone is in state 1, right? So in state 1, we pass it through a cavity of oscillating electric field, right? So this cavity has a length of L, which I purposely designed this to be. L is equals to 2k minus 1 pi h bar V over 2pe0. So this is only true if we know the speed entering this, but this is a slightly difficult problem. But if we know the speed, then I know how long to build my cavity. Okay, so if I build it this long, then every atom that comes out, the minute it comes out is in state 2. Okay, so it enters at state 1, it exits at state 2, so energy has been lost. That means a photon has been emitted by h bar omega. So if many atoms enters in state 1 and many atoms in state 2, so we have created many photons having this frequency, and we can use this to emit a beam of MASER light of h bar omega. So this is how a MASER works, right? This is specifically an ammonia MASER, but as I had shown in the video last time, in the previous class, right? What the lab was doing is they use a diamond to create the MASER. No, was it diamond? Some carbon structure, right? But they do it in a slightly different way. But the main point is they want to create all the state in this form and eject the state in this form, and you collect a bunch of photons and you will create this MASER light like this. Yeah, C60, the carbon structure, right? Yeah, so yeah, you remember. I forgot already. And then the device is like very small handheld thing, right? So they put this, they shine the green laser to excite the atoms. They use another laser to do it. So that is also another thing. As the technology develops, you have laser, you can use this laser to build another laser, and so on and so forth. So like the nuclear bomb, you know, like the hydrogen bomb, to trigger the hydrogen bomb, you need another plutonium bomb to do it. But once you develop a technology, you can expand very fast, right? Develop the complication. But there's some slight issue. There's some additional issue which we will not solve here, but I should at least mention this, right? Because we are dealing with a real life problem, so we should at least know the issues. V is like, because it is a beam of atoms, so not all atoms have the same V, right? So that is a problem. But you might have learned this before. The values of V follow. You have learned this in the thermodynamics, I think, the Maxwell-Boltzmann distribution. Right? So I guess it's usually, you know, the cavity should follow the V with that is the highest in the distribution. Right? Because the Maxwell-Boltzmann distribution is a stream of particles, right? Not all particles have the same V, so it follows a probability distribution. So the number of particles following the distribution is this. So maybe you get this. So that means not all the states have the same V. So those who are moving slow or those who are moving faster, right, they may not have the 100% chance to eject the photon. They do not have the 100% probability to come out as state 2, right? But you choose the highest, then you get the most number of states coming out as state 2, then it is the best you can do, right? At least you collect enough atoms. So these are like the challenges when you deal with one system. You need to solve the problem coming from another aspect of the system and things like that. So, you know, if you work in experimental physics, these are the things you worry about, right? And this is why our math was very problematic, because this system is specific for resonance, right? So even if you use the math, we are only solving it for this particular case, and we have many other problems to solve already. So that is like the challenges in building a MASER or ammonia MASER, or in general some kind of optical device, right? So if you deal with quantum technologies, these are the things that you need to do. Okay, yeah, so any question? I guess we have finished chapter 2 already. So that's how the ammonia MASER works, and I hope you think it's as cool as I do, right? This is a pretty amazing stuff that people have been doing this since the 1950s. So today's technology is even more advanced and more ingenious solution. People have come up with even more ingenious solutions since then, and now we can do like many other things. Yeah, you can build lasers of any lights frequency choice that you want, all kinds of things. Okay, so with chapters 1 and 2, we have kind of gone through the abstract theoretical study of vector spaces, you know, and then Schrodinger equation postulate, like all these are very math and abstract stuff, but in chapter 2 you see that we can actually use this in a real life experiment, right? So it's kind of unfortunate that we are in a pandemic and we don't have physical class. We do not even have equipment to show you that the real thing that people can actually do with it, but at least you get an idea that these are the real things that people are doing, and we can use this to build the MASER. So we have finished chapter 2 with this story. So next week we will move on to chapter 3. Chapter 3 will be a bit more math, and then suddenly we will come back to familiar things you have done earlier, like the potential well and things like that. So that shall be our plan for chapter 3. Yes, Jia Cheng. Infinite states. So it sounds scary, right? Infinite dimension Hilbert space. But it's actually something that, if you take modern physics, is the potential well. The potential well problems. The potential well is an example of an infinite dimensional system. So it's just the word that sounds scary. Okay. So yeah, that's all for today. Then see you on Thursday. So our Thursday class, if you are attending the astrophysics talk, we shall start at Thursday 4:30 p.m. roughly around there. Okay, then Thursday 4:30 p.m. So see you then. I will stop the recording.